Hello students and welcome to today's lecture, which is going to be on the equilibrium constant, which to be honest is just going to be a constant that we're going to use to kind of show the equilibrium point for a whole bunch of reactions at a constant temperature. Okay, and it's kind of like our numerical way of trying to express what's going on with equilibrium. And for the most part, what we need to be able to do for these types of equations are going to be to set it up and then be able to plug in numbers that are usually given to us. And in general, the setup for this is actually going to be fairly simple, but you're going to want to make sure that you take some good notes so that it's fairly easy here. Okay. So essentially what we're going to do with each equilibrium constant is that we're going to go ahead and split it up into the forward reaction and the reverse reaction. Okay, and this is kind of an arbitrary designation, especially since it is equilibrium, but usually whatever thing is the easiest one that you want to the easiest compound to get a hold of is going to be the thing that you're going to have for your forward reaction. Okay. And then your reverse reaction, again, is going to be just the reaction that's going in reverse. And essentially what we're doing is we're trying to compare these reactions kind of reaction rate style, where we're going to compare the forward reaction in conjunction to the reverse reaction. Okay. So we're actually going to be comparing the two rates, okay? And so this is going to be essentially the rate going forward, and this is going to be the rate going in reverse. Okay. And what I want you to notice here is that we're going to always put the forward reactants on the bottom, and then the reverse reactants are going to end up going on top. Okay. And this is going to be as long as the temperature remains constant. Okay. So this is a case where we're going to have to make sure that T is constant in order for us to go ahead and calculate it through. And that's one of the requirements for figuring out the equilibrium constant going forward here. Okay. To generalize, the formula for this is that we're always going to have our reactants at the bottom, and the coefficients that come from the balanced equation is always going to end up being the exponents here. Okay, so the coefficients are going to end up being the exponents for our equilibrium constant. Okay, which means that we can go ahead and take a look at a couple of these, and in general, as I said, we're just looking to write what the equilibrium constant for these are going to be. Okay, so for this first one, which is A, and if you want to go ahead and try and write the initial equilibrium constants now on your own, go ahead and pause the video and take a little bit of time to work it out. Okay. And for those that just want to go ahead and watch through it, we'll go ahead and start and continue. But basically, this is our reactant. It's on the left. So we're going to have O3, we're going to put it in brackets, and then it'll be squared. On top, we're going to have O2, it'll be in brackets, and it'll be cubed. NO2 will be on the bottom, it'll be in brackets, it'll be squared, and we'll have it with Cl2, which will also be on the bottom in brackets, all over NOCl, which will end up being squared. Okay, Ag plus is going to end up being on the bottom with NH3 squared all over Ag NH3 2. Okay, interesting compound. All right. So again, this should end up being what you end up getting here for your reactions. Okay, this is the same thing as I was stating before, except it's just easier to see now. O3 on the bottom and it's squared. NO2 on the bottom, or sorry, NO, it's on the bottom, it's squared because it has a 2 in front, and it's next to the concentration of Cl. And this one over here is NOCl, it's squared and it's on top. Same thing goes for this one, Ag, reactant, it's on the bottom. NH3, there's 2 of them, therefore it's squared. And AgNH3 2+, there's 1 of them, it's right on top. Okay, and this is just, essentially saying like, oh, okay, what's the comparison between the concentrations? Okay, so notice that this is our concentration of these two. Okay, and this is just, essentially us trying to compare those concentration amounts. Okay, you can go ahead and attempt to do these ones here too. So A and B, go ahead and pause it so that you can attempt A and B right now. Okay, I'm going to assume that you have done A and B. So you should have HI, and then it should be squared over H2. And I2, there's no coefficient in front of either of them, so it ends up being exactly that. Here, CD2+, BR4 will be to the 4th because there's 4 of them. This one, there's only 1, and that'll give us our equilibrium expression. Okay. Now, equilibrium is going to be something that's going to end up being reached from either direction. Okay. So I want you to go ahead, and this is essentially our equilibrium expression, but this is and how we make the equilibrium expression. But I want you to notice here that when we go through and we do this experimentally, that the ratio between these two ends up being the same no matter where we ended up starting at. Okay, so 0.211, 0.211, 0.213, 0.213. Okay, so these end up having about the same numbers. Okay, so with experiment 1, what I want you to note that they initially took 0.0 moles of N2O4, and they added to that 0.02 molar NO2. And then after it reached equilibrium, we ended up getting the equilibrium constant of this right here. Okay? So it's an equilibrium constant because no matter what you start with, once you reach equilibrium, all of your numbers are going to end up equaling that right there. Okay? And remember, this is for a constant temperature, so this changes with temperature. Okay, reaction 2, it starts out with more NO2 than reaction 1. And notice that we ended up getting the same amount, okay, 0.211. Reaction 3, we end up having twice as much as 2, and we end up getting the same kind of ratio that's going on here, okay. And then finally, reaction 4, we end up with 0.020 moles of N2O2. And what you'll notice is that we get the same kind of equilibrium expression, okay? And this should make sense that, the final amount of equilibrium, when we reach equilibrium, it doesn't matter what we started with, the forces that are forcing us into equilibrium eventually are going to reach that final equilibrium point where we can go ahead and where we're making both at the same amount. And it doesn't matter what we started with, our equilibrium point is always going to end up being the same. Okay? And this is just trying to show graphically what's happening here with the N2O2. Okay? So in experiment 3, we had a lot of N2O2. We started with a lot, and we ended up reaching the same equilibrium point, and this is just showing it graphically. Okay? And this is showing the exact same thing, but it ends up showing it with our classic Haber-Bosch process, where we can go ahead and start with a lot of hydrogen and a fair amount of nitrogen, and we will start with 0 NH3, and we'll end up getting to this exact point. Whereas if we start with a lot of NH3 and we don't have much nitrogen or hydrogen or zero, we'll still end up getting to the equilibrium point, because that's just the point at that temperature that they have reached equilibrium. Okay. So the next thing is going to be talking about K values. Okay. And before we start here, looking at this, K values are essentially concerned with this type of expression. And if you notice, like mathematically, if K ends up being really, really big, well, then it's going to favor the products. If you have a high concentration, if you have a high concentration of your products, or your equilibrium constant is really high, that means that it favors going towards the products. Likewise, if your K is really, really low, you're going to be favoring your reactants. Okay? And I feel like this is easier to look at mathematically here, that if this concentration is high, well, obviously you're making a lot of your products. If this one is really high, well, K is going to have to be low to indicate that. You're making more of your reactants. Okay? So if your concentration, and these are just the concentration numbers, or basically how much of each compound that there is. So that one is just going to be something that you're going to end up, looking at, looking forward. For the most part, it's going to be the types of questions are going to be, does this particular graph or information say that the products or the reactants are favored? And you would basically just have to go ahead and look at the K value and see whether it was greater than 1 or less than 1. Okay. And in this particular case, what you'll notice is that we have... Okay. So the other thing that's sometimes done, and I'm showing it to you not because we're going to be using it a lot, but because it's something that you may end up seeing later on, and that's this idea of K prime. So this is the reaction as it was. If we flipped the reaction and decided to go the opposite way, we end up calling that the K prime reaction. And that's just the reaction going the opposite way. So this is going to be something that you may hear of if you go into another chemistry program, especially if you're going into a college level chemistry, that I want you to be aware of. That K prime is just K, just flipped the other way around. Okay. And in this particular reaction, we can see that at this particular temperature, we can see that this is less than 1, so it seems like the reactants ends up being favored here. Here, we see that the total ends up being more than 1, okay? And since it's more than 1, we can say that the products are being favored here, which makes sense because, N2O4, okay? Yeah, and that's going to be it here. I'm not certain that this is anything that we're going to end up worrying about here, because I don't think that we're manipulating so much. Again, the main thing that we are going to be concerned with our equilibrium constant is being able to write out what our equilibrium expression is going to be, and then to be able to find what the equilibrium constant is. And in general, what will happen is that I'm going to end up giving you guys the concentrations. And to figure out these concentrations, you'll just literally have to plug these numbers into these equations right here. And then you'll just have to do the actual arithmetic in order to solve them right there. Okay. This should give you the information that you need to finish your worksheet for this section. Okay, and as always, remember, stay lazy.